Okay, welcome back for our third Loeb lecture. Probably if you're already at the third lecture, we don't need too much of an introduction, but again, we're happy to have Asimina ARVANITAKI here from the Perimeter Institute, and she's going to pick up where she left off yesterday, telling us more about detecting the cosmic neutrino background.
Yeah, so, okay, so we'll start from where we left off yesterday. So at the end of the lecture yesterday, I hoped I had explained to you why a rod, a piece that has a length L and a width W, acts like a diffractor of cosmic neutrinos and produces an asymmetry between neutrinos with antineutrinos that have index of refraction larger than 1 inside the material and neutrinos that have index of refraction less than 1 inside the material. That kind of looks like this, okay? And so far, I have assumed that the neutrinos that hit the stick are one momentum, and they move paraxially, okay? So that's why you get this beautiful wavy pattern. So of course, neutrinos are not single momentum, and they don't move in one direction, okay? They come from all directions. So let's try to put everything together and see how we got to that sea-urchin picture. The other thing to keep in mind is that the effect that I will strictly describe is a wave effect. So the distance at which this maximum of the asymmetry appears is related to the width squared over the wavelength of the neutrino. So if I were to take the wavelength to 0, this distance will go to infinity and I will get 0, okay? That's very important to remember. And this is how it will look if we take, and the width of the asymmetry at the optimal states of order the width of the stick. So first thing to do is the simple thing to do, first of all, is to take into account that the momentum of the neutrinos incident on the stick is not monochromatic, okay? And it obeys a thermal distribution that follows a massless Fermi-Dirac statistics. And so you do an integral of the form that you see up there. And what happens now, before you have the nice wavy effects, all those things disappear. So the asymmetry far away from the stick goes to 0. But you're still left with a bright spot in the middle. So the fact that neutrinos are not monochromatic does not erase the effect. Part 1, very important. It does suppress the size of the overall asymmetry by a bit, but it doesn't change qualitatively what the signal looks like. And I should remind people, actually, is there? Yeah. So brighter means larger asymmetry. Okay, it is on. So this is brighter means larger asymmetry. Dark blue means the opposite sign asymmetry, okay? So of course now, neutrinos come from all directions. And this is where the naive idea of the sea-urchin came about. So you take, okay, the first thing you do is you think, put all the sticks on the surface of the sphere, and make sure that the center is at a distance from the face of each stick so that W square of some sort of average wavelength of neutrinos sits at the center. Turns out the optimal value for this lambda averager, if you plan the numbers, is like 3 millimeters. Let's call it some RMS range for the neutrino wavelength is between 2 and 4 millimeters. So this is the type of setup, and I'm showing just a cut of it. So now we need to see what it does. So an important thing to note is that, well, most of the time, in fact, if you arrange the sticks with distance W with a width W, you have a little width W1. Turns out most of the time the rays, the neutrino waves, their axis of propagation comes in between the sticks. Okay? So, so the paraxial case that I discussed before is kind of like an optimal case scenario. So what you do is you apply, though, the same procedure. So in order to calculate what that does when the rate comes in between, so you take the wave, and here it comes, so this is the extreme case where it comes right smack in the middle between two sticks. And you find, in order to calculate how much phase is accumulated by the wave at the end of the sticks right here, at the end of the surface right here, you calculate the optical path, basically the length that is traced by each ray of the wave as it goes through the structure. And you get something that looks like this. This is the length in meters, and this is basically the distance x here. And it's not centered at 0, because as you see here, it's not centered at 0 either. And then you want to see again what your pattern is at D. So you do the same Kirchhoff integral that we did before, but now you find that instead of an axis right in the middle, you get something that is on the side. And there at the center, you get a small, actually, axis of the opposite sign. Okay? But overall, qualitatively, it looks like each rod still acts like the same way like a single rod does, but it now shifts where the pattern appears. So now we need to sum over all incidence angle or average over all incidence angles. And we need to choose the rod again. Actually, and I forgot to mention before, let's see if I can go back. So here, in order to make sure that no matter the incidence angle, you maximize how much optical path you acquire as you go through the sticks, turns out that L has to be of order R. If you make R or larger, so if you make R much smaller than L, these things open up, and a lot of the time you just see the sticks at an angle, and the effective path that you see is really small. So that suppresses the effect. So yeah, we're here. So now we need to average. Again, the width is just a parameter that is determined by the radius of the stick. Now, in order to do the averaging, turns out we don't need to average over all angles. And the reason is the structure is periodic. Okay? It has a period in solid angle that's roughly the width of the stick, the distance between the sticks W1, divided by 2R, the whole thing squared. Okay? That's roughly the solid angle of each of the periodicity of the structure. So as long as we calculate what the asymmetry is given by average over this solid angle, we're kind of done. And the way you average is taking the C3, this sine theta, and then, in principle, you need to add all solid angles like this, but the pattern remains the same. So what you end up with a final neutrino distribution that is radially symmetric if there is an omnidirectional neutrino flux. Okay? We're all good here? Did I go too fast? No. Okay, good. So this is how the final thing looks like. So even though neutrinos come from all directions, by arranging the structure to have this sea-urchin type of thing, I still end up with an excess of neutrino close to the center. Now, an important thing to note is that in my calculations, I actually don't know what the distribution of neutrinos is away from the center, because the approximations that I've used when I did the Kirchhoff integrals, I only care about the region very close to the center. Okay? And it looks like this. Again, hot spots mean, brighter spots mean higher asymmetry. And because the rays come in between most of the time sticks, this is why now what you thought would be an excess, you would get a maximum at the center, it actually kind of moves to the side of the setup. And again, this is the parameters that we considered. we picked different materials. So for the biggest one, we picked iron because it's one of the most abundant elements that we have. I think, as I said, I'm a big fan of depleted uranium because it's basically trash that you can use for this. And it has all the nice properties that you want to maximize the index of refraction of neutrinos. And this is the type of diffraction pattern. This is how we arrived to this type of diffraction pattern that I showed on Monday. So this is for the 2 meter, 10 meter, 100 meter iron setup. And as I said, I only assume one massive neutrino. I fix the mass to be 0.1 eV, and it's hidden by here somewhere. And the yellow line corresponds to a mu and tau neutrino excess, and the blue line corresponds to electron neutrino excess. As you can see, electron neutrinos couple usually much less than the mu and tau neutrinos, and they have the exactly opposite sign. So now let's look at this a bit more carefully now. And I pick the, here I pick the 10 meter tungsten structure. So the takeaway message from all this sea-urchin thing is that it only works, by the way, in the linear phase, in the small phase approximation. So if the neutrinos, if you make it too big, all the approximations that I talked about will completely fail. So as long as the momentum of the neutrino k times delta, the difference of the index of refraction from 1 and L is much less than 1, then the asymmetry that you get, the maximal asymmetry is of that order. So it grows with the size L of the structure till, again, the small phase approximation breaks down. The size of the gradients, the wiggles that you see, are set by W, and that's not because of any property of the neutrinos, but because this is how we design the structure. So W, actually, this whole shape of the structure also determines the size of the gradients, okay? And the overall size of the structure, is related to the width because we need to, basically because of diffraction. So this is where we get to the part that Melissa was asking in the beginning. So what have we gained? What have we done? So how would you go about even imagine detecting such a thing? So there are different ways. So the one I think right now is the most obvious. You take a mass and you put it somewhere in the region where the asymmetry, where the asymmetry is created, okay, close to the center, not necessarily right at the center. And then, because now the density has a gradient, the interaction energy between the neutrinos in that region and the mass will have a gradient, and there's going to be a force, okay? And because the sticks actually, the rods create an excess of the neutrinos, the type of neutrino that's attracted to matter, it means that if I put a piece of mass there, that mass wants to be pulled, the direction of the force is such that it goes to the place where the asymmetry is maximized, okay? Because of the nature of the setup. The mass needs to be made of something that has huge atomic numbers and high densities. So you can make it actually, tungsten is a great material, gold is actually the best, because it turns out it has very nice properties for many of the things that we're discussing. And the force will always be in the radial direction for a single object, okay? Now, if we wanted to make, there is a way to convert it in a force. And the way you do that is that if I were to plot, and we don't have to change, where is the chalk? Here? Keep going, keep going. here. Sorry, I'm lost. Oh, it's there. Okay, okay. Sorry. Yeah. Found it. Sorry. Oh, it's hidden. Okay. So basically, if you were to look at the center, this is the center of the structure, and you have the sticks going all around. What you will get if I were to plot the surface of constant force, it will look like a circle. Okay? So if I were to put a mass shell, what the force would want to do is to just pull it apart. It wouldn't want to spin it, but it would want to pull it apart. Now there is a way to convert this force into a torque. And the way you do it is by taking, for example, like a stick, and you attach two different masses on the edges. Am I making it too small for the people in the back? It's good? Okay. So you put two different masses. One is gold, for example. One is tungsten. And because these are different compositions, they will feel different force. One of the great things about the neutrino force is equivalence principle violating. So it cares about the composition of material. So this guy will feel a force of one size, let's say this way. This guy will feel a force of a different size this way. So overall, this wants to spin. Okay, you would want to, this way, I guess the way I've drawn it, it will go this way. So you can convert this, what appears to be some conservative force, because it's the gradient of a conservative potential, you can convert it into a torque by using what is essentially a torsion balance. This is what the torsion balance does. And this is what the force field looks like. If I assume that I have a 10 centimeter tungsten mass, and I take my best case scenario to maximize the signal, I assume I have either a muon or a tau neutrino of mass 0.1 eV, and I'm using the biggest structure that I assumed, which is 100 meters. And turns out that this is a small force. You see there the axis is multiplied by 10 to the 28 Newton. Just to give you an idea, again, the mass, the weight of a proton is 10 to the minus 26 Newton. So this is 100 times smaller than the weight of a proton on the Earth. Okay, this is small. It's not huge. But nevertheless, it's still 3 orders of magnitude larger than the force that the Earth gave us for free. So these effects dominate over the Earth. And it's also 4 orders of magnitude larger by other things that can give you a constant force, which is coherent scattering. Okay? And what is coherent scattering, for those of you that don't know, is the following process. So if I have, let's say I have a bunch of atoms, and actually we can make them into a lattice because we have a solid. So if I have a particle coming in, and they interact with, they get scattered from this object. If the momentum transfer is much smaller than 1 over the interparticle distance, which is this, then I will couple like the charge is coherent. It's like if I have 4 particles here, the cross-section will go like 4 squared. So I see like a single charge. I see like a single object. So this is what is known as coherent scattering. And because the neutrinos have a macroscopic wavelength of a millimeter, it means that if you scatter with material, you will coherently couple to roughly 10 to the 20 atoms that are inside within that millimeter. The problem, of course, that you have to deal with is that the momentum transfer is really small because it's of order 1 over millimeter. So people have calculated, and because neutrinos are moving in one direction, we drift through the neutrino radiation. There is a relative velocity of the solar system with respect to the cosmos. to the cosmic neutrino background, there is a preferred direction for scattering. So that gives you a constant force. So, or a force that modulates annually and daily, of course, but the problem with, as you know, many things modulate annually and daily. Nevertheless, it's there, but it's still 4 orders of magnitude smaller than I just showed you. So, so we've gained quite a bit, okay? First of all, we know now that, that those no-goes that were said in the 80s, it's easy to evade. Not only that, we've managed to enhance that force by several orders of magnitude, many, many orders of magnitude. Another thing to keep in mind is that I told you that the size of the asymmetry grows with the size of the structure, but because we need to adjust the width of the structure to get the right focusing or pattern of neutrinos, diffraction pattern of neutrinos close to the center, the force actually grows with the square root of the length. And the reason is that the force, so the force is proportional to the length of the sticks, the phase that is accumulated, but it goes like 1 over the gradient, which is set by the width. And this width, in order to maximize the effect, has to go like 1 over square root of L. So it means that this grows like a square root of L. So in fact, you don't gain as fast with the size as you might have thought. So if the optimal thing would be not to build necessarily a 100-meter object, but choose very dense material, like, that's why I really like depleted uranium. If you were to make the biggest structure possible out of depleted uranium, it would give even bigger gains if you were to build something much bigger out of iron, okay? So now we're here, and now we go, okay, how do you detect a force that's 100 times smaller than the mass of a proton? And the answer is we cannot detect it yet, okay? We are about 8 to 9 orders of magnitude away. But the nature of the force points to a certain class of experiments. And there is 2 main types, and you see 3 pictures here of those experiments. The one that has been extremely successful so far in detecting tiny forces is the torsion balance, okay? It's basically what I've drawn here, where you have 2 pieces of different matter connected by a stick. Of course, as you can see here, this is a bit more elaborate. And these are the 3 people that actually got the breakthrough prize a few years ago. This is Adelberger, Blaine Heckel. I'm going to mess his name probably, Gundlach, if I pronounce his name correctly. So these 3, with their torsion balance, managed, first of all, for a while, they had the best test of the equivalence principle. And this torsion balance also allowed them to test look for free forces very precisely. Now, the annoying thing is that they've managed to control all their systematics below, and their thermal noise limited. So they operate this at room temperature. You actually, if you go to their lab, you can see it. The annoying thing, of course, for neutrinos is that they are still 8 orders of magnitude away from where the signal is, okay? Interesting thing is that Markus Aspelmayer in Vienna is getting interested in the topic, so he's building his much smaller torsion balances and starting to play around with it. So this is one interesting direction. So I should point out that these guys are very far away where the quantum limit is. That's the other thing. Another thing you could do is actually not use a torsion balance that is suspended by something, is actually use a harmonic oscillator that is not attached to anything. And it's actually suspended with quadruple types magnetically. And this is a picture of an experiment of much smaller scale that you see here. People can use lasers to do this, but if you want to trap an object that's like 10 kilograms, because this is what you will need to do, you will need a quadruple, like one of those quadruple magnets that they use at the LHC. So this thing would be like a huge magnet, very powerful, and you have a small region at the center where it would be trapping this object, okay? And of course, you'll have to find somehow cool it, and you'll have to do all these fancy things on it. So the question is, what would be a possible benchmark? And usually, that benchmark is set what quantum mechanics limits you are able to do. And this is what people call the standard quantum limit. So if you were to take a harmonic, that harmonic oscillator and put it in its ground state of motion, and here I've used parameters like, this is the type of mass you would need for a 10 centimeter tungsten mass. It's 20 kilograms. Tungsten is extremely dense, one of the densest things we have on Earth. If you use a trapping frequency a bit below where torsion balances operate, and a Q factor a bit above where torsion balances operate, and a very long integration time, there it is, the 10 to the minus 28 Newton. So the standard quantum limit, now the force that we've created through this structure does not appear to be far from the standard quantum limit. Do I have a proposal again? No, but at least the benchmark, the naive benchmark that you would set for yourself is at least now satisfied. Before, we were not even near that. Now, the standard quantum limit has the other property, and we can give an entire lecture on that and how these things are derived, has the other thing that it actually depends on how you do the measurement, okay? So this is if you have a harmonic oscillator that's trapped in this frequency. Now, if you were to measure, take the torsion balance, similar to what you saw in Adelberg, and put that in its ground state of motion, you will see if you convert the numbers, you can actually do slightly better in measuring. So the standard quantum limit for those is a bit better, keeping the same parameters. Q factor, improving slightly the Q factor, keeping the same, how does it call, rotational constant. But still, as I said, they're not there. Okay? They're definitely not there. So this will take some time if it is to work. It will take definitely time. But at least now there appears to be a path. So I hope now it answers this people's question of what type of experiments you do. Okay? Yes, question.
Don't you afraid from the back reaction of the detector on the interference pattern?
No, no. Because the width of the detector is 10 centimeters, right? The whole width.
But you had the magnet of LHC magnet there.
No, that's small. It's not the full dipole. It's the quadruple are much smaller. So though any material you add close to the thing, it's not going to be too much most of the time. But in principle, yeah, you should take that into account. Yes?
Thank you.
Melissa has a question.
Just on the quadrupole.
Yeah.
I mean, the quadrupole focuses in one direction, so how do you?
Yeah, you have to do some weird thing. We're discussing this with Andy Geraci. So there has to be, but this is the type of size you would need, just to give you how strong of a magnet you would need.
Because the ball would go flying in the other direction.
Yeah, yeah. So yeah.
Sorry.
Yeah. So yeah. So that's why I'm saying this is a work in progress. It's not like we have, but it gives you an idea of how big of a magnet you would need, because you need to suspend. What actually you want to do, actually, the reason that you need such a big magnet is because you need to overcome the gravitational pull of the Earth. So one direction of the trap needs to be very strong so that the thing doesn't crash to the ground. But the other direction needs to be extremely floppy, so you have this low trapping frequency. Okay? So it's a very type of special trap that you would need, okay? So, yeah, it's not going to happen tomorrow. So, okay. And other questions? Good? Okay, carrying on. So, so now this is again, this is a force, now in units of 10 to the minus 5 as a function of the neutrino mass. This is a plot that suggests how one should present the result, because as I increase the neutrino mass, the size of the signal grows. And this plot also naively takes into account some clustering effects, which are more important for heavier neutrinos. Again, as I said, if you want to ignore cosmology, then this full range is all okay for the heaviest neutrino mass. If you don't ignore cosmology, then you're right here in this little corner right here. Okay. And the standard quantum limit that I showed you here is there, right there. So naively thinks there's a glimmer of hope. I mean, I don't want to call it, oh, yeah, celebrate, but because the experiment is extremely hard and we are far away from it. But you see now what you can do and how a possible way to present the results as you progress, right? Because this won't happen overnight. So now let's switch a bit gears. Okay, question, yes?
Sorry, so if we do take cosmology into account, then it seems like we would have to somehow go below the standard quantum limit in order to see it?
No, so there is a range. So it's right here. So this is below 0.1 where they cross, this guy cross. I don't think you have to do much below the quantum limit. It's within factor of order 1.
Okay.
So this is not, these are all pretty close. And this, I mean, depending on how you measure this move, these are all like, if this is 2 and this is 3, right? So we're taking about 50% difference between the two signals.
Okay, so it's a bit of a race.
Yeah, it's a bit of, I mean, yeah. So, yeah, it's close. Like, because I think actually it's a good thing because the mass, because delta m squared, the difference of the neutrino masses that we have measured tells you there is a lower bound of about 0.05 eV. Essentially, we know the mass of the heaviest neutrino essentially within a factor of 2 or so. So that tells you what the size of the force changes. So, and there is some clustering effects that can also help a bit, but it's not a huge range. It's not orders of magnitude. Factors of once you are there, factors of a 2 you can fight for, which is okay. The question is, how do you get there? So, okay, now, yes, okay.
Maybe you're going to do this later, but are you going to talk about Majorana neutrinos?
No, I will not. You can ask me about them. I can tell you about them. So this is something that we are thinking about. And Majorana neutrinos, as you know, are tricky. If I have one Majorana neutrino, it means whatever I'm talking about is velocity suppressed, right? And probably by 2 powers of the velocity. It turns out to be 1/50 squared, probably. But now, if you have more than one flavor, then you can have all sorts of different effects going on. So this is the thing that we are still thinking about. So there is going to be a range. So it will be what it will be. And hopefully we'll know soon. Yeah, little Majoranas, yes. Okay, good. So, so with Savas, we decided to focus on the cosmic neutrino background because we know it's there. So, and the stakes are different, right? When we talk about cost, someone asked about the cost of the structure yesterday. And the scale, the money, if you know something is there, the money you would put in to find it, we're talking about different scales. Take CMB experiments, for example. People put essentially billions in them. So the scale of these experiments, the amount of money you would put, it depends. So because the signal is there, then it puts it in different perspective. Now, of course, the natural question one can ask is, OK, what else can you use this for? And the obvious thing is, what about dark matter? OK, and for us, dark matter was an afterthought in many ways. And for this, I'll have to switch gears a bit and give you a little spiel about dark matter. A more general spiel, and it will make it more obvious about the type of candidate of dark matter we chose to consider. So first of all, we know dark matter is there. From its gravitational interaction, good old CMB told us so. Another observation, galactic rotational curves told us so. There is a component of matter that doesn't behave like baryons, interacts with us gravitationally, it's non-relativistic, and it helped create our galaxy. So it's 5 times more dense, 5 times more abundant than baryons. And we don't know what it is. We only see it through the force of gravity. So first questions you are, what is dark matter made out of? And if you try, and if you ask, and this is something that's a very favorite topic of particle physicists, and every particle physicist basically has their own favorite dark matter model. Okay, we have tons of models. So if you try to put, to quantify how many models of dark matter we have, you will see that the dark matter mass range covers some 70 orders of magnitude. Okay, on the lower end, the bound at around 10 to the minus 20 eV, which, just to give you an idea, is 30 orders of magnitude lighter than a proton. This is extremely light particle, which means that its de Broglie wavelength becomes so large that it now cannot fit inside galaxies anymore. Okay? So it doesn't form structures the way that we see them. Now you can make the dark matter heavier and heavier and heavier. At some point you cross the Planck scale, so it becomes to have either primordial black holes or composite particles. And then you hit another wall at around of a fraction, depending on what measurements you take, at around a fraction of a solar mass, because then the dark matter becomes too granular to observe the structure that we see. Okay? So this happens in all 70 orders of magnitude. And people have populated with all sorts of ideas that entire range. Next question you ask is, well, you have your favorite dark matter candidate, you should ask your friend is, how is dark matter produced? And in fact, this is where most ideas fail. So a WIMP, a weakly interactive massive particle, became extremely popular because if you have a particle of mass of 100 GeV that couples with the strength of the weak interactions in the early universe, and it's in thermal equilibrium, its leftover abundance today has roughly the measured density. Okay? And people, rightfully so, built and continue to operate experiments trying to look for WIMPs. Another type of particle that we'll talk about are axions. Now, the other question you ask is, does it have interactions other than gravitational? And usually when you have a production mechanism, you know it couples to the standard model. So you can reverse the question, and usually the answer is yes, it does have other interactions. There's another question that you can ask that I haven't put here that it tells you, so what is it motivated by? Does it solve any other problem other than being the dark matter? And in that sense, the WIMP is still special because it's related to the hierarchy problem. And there's another particle that's also special. It comes by the name of the QCD axion. So in the standard model, you can write this term that mixes electric field of the strong interactions, the magnetic field of the strong interactions. And if present, it would create a fundamental electric dipole moment for the neutron. Okay? This is fundamental breaking of symmetries in the standard model. You break these coupling breaks charge and parity symmetries. Oh, I forgot to unclick that. Its mass, so this parameter here, this theta parameter tells you that it should be order 1, but we've only considered it to be 1 part in 10 to the 10, and this is how the axion was born. So people turn this theta into dynamical parameter, and its value dynamically relaxes to 0. Now the axion mass is much lighter than any of the particles that we know, even lighter than neutrinos. And its properties are given by a single constant, the axion decay constant. And it has a Compton wavelength if the axion decay constant is around 10 to the 9 GeV. It has a Compton wavelength of 30 microns, or a de Broglie wavelength, turns out, of about tens of centimeters. Okay? Turns out if you go to extensions of the standard model, axions can be more generic, or particles like the axion. And this is where the idea of string axivers come into play. So if you, in string theory, there are 3 ingredients that are essential for the theory to make sense. You need extra dimensions. There are gauge fields that live in these extra dimensions. And there is topology. Basically, you need to compactify these extra dimensions to give rise to a 4-dimensional world. So, and these dimensions can be compactified simply on a sphere or on a torus. And the way you compactify them is just limited by our imagination. Turns out, combining these 3 ingredients, having these gauge fields living in these compactified extra dimensions, give rise, these gauge fields manifest themselves as massless particles in our 4 dimensions that have properties similar to axions. And the way to understand this is the following. So there is a nice analogy of this with the Aharonov-Bohm effect. So the Aharonov-Bohm effect, you probably heard it in your quantum mechanics class. If you take a solenoid threaded by a magnetic field, and you take an electron around the solenoid, you find that there is a phase that the wave function of the electron has acquired, even though it is in a region where the force on it is 0. Okay? This is an example of a topological effect. So there is no force, yet nevertheless there is a non-trivial gauge field configuration of the electromagnetic field around that creates a phase for the electron. Now there is no force on the electron, but it still took some energy. So the energy stored outside the solenoid is 0. It still took some energy to create the configuration in the form of the magnetic field stored inside the solenoid. So let's turn this by 90 degrees. And turns out that in string theory, a similar thing happens. The way these extra gauge fields that live in these extra dimensions are similar to the electromagnetic configuration, the Aharonov-Bohm effect. The very important difference is that because you have complex topology, you can create holes in the geometry of the extra dimensions that remove the region that carries any energy. So from string theory, these topological configurations manifest themselves in 4 dimensions like massless states. And because, of course, they're massless, they carry no mass. They carry no energy, so they carry no mass. Turns out that you can have an argument that I think Matt is trying to sharpen quite a bit, that you can actually, they still get some small corrections to this mass that are exponentially small from string corrections. But if you want to have the QCD action in the spectrum, it tells you that those corrections have to be small. Okay? So you can have a lot of very light axions coming again with a QCD action. Now, I told you that it has a good production. Axions have a great production mechanism, which goes by the name of the misalignment mechanism, but we don't have time to discuss it, so I'll skip this. So even though axions are more, and you can ask me about it afterwards if you want to explain it, even though axions, as I said, are more generic, I think the QCD action is the more pristine of all, because it has It solves a specific problem. It has a well-defined parameter space. So its parameter space is just a line. It's just set by the decay constant. So this is what you see here, the parameter of the QCD axion. Below 10 to the 9 GeV, this decay constant is excluded by stellar cooling and supernova observations. Above 10 to the 19 GeV, we exclude that range basically because of common sense. We don't think you can have decay constants much larger than the Planck scale. But, I mean, they make perfect sense if you just write them down. Okay? An interesting thing, so I think that I don't have time to talk about, but I'm extremely proud of, so I had to put it in there, is the effect of black hole superradiance. So there is a cool thing that can happen for the QCD axion, in fact for any axion, when their Compton wavelength becomes of order the size of astrophysical black holes. So there's this cool effect called superradiance that can cause them to spin, can cause the black holes to spin down and creates a cloud of axions around the black hole that can emit gravitational waves. And you can do searches for it, for example, with experiments like LIGO. Okay? So that's something that we can discuss more of later, but it's really, if I were to put, I could give a talk about this because it's really fantastic physics. Yeah, it would be, that's something I can just talk to you on the board afterwards if you want. So how does, now let's go back to our sea-urchin and discuss what does the QCD axion, how does the QCD axion, if it is dark matter, get affected by the sea-urchin? So the important thing to note for the QCD axion is that when it goes through nuclear matter, it feels an interaction potential. And the reason that it would feel that interaction potential is because it needs to couple to nuclear interactions to solve the strong CP problem in the first place, to explain why the neutron electric dipole moment is so small. Okay? So this is the interaction potential of the QCD axion as it goes through matter. It's proportional to the density of the atoms. It's proportional to the number of nucleons that each atom has. The rho, this is number density, okay? It's inversely proportional to the axion mass, inversely proportional to the axion decay constant, and there's this pesky constant here, sigma nu, which people calculate from nuclear interaction, from QCD matrix elements. And it has a size 60 MeV. Just to give you an idea, the mass of a proton is 938 MeV. Okay? And this force is attractive. It doesn't matter for the axion, the effect that I will describe would work either way. It turns out that this interaction is attractive for the axion. So the axion, turns out this is like a correction to the axion mass. So the axion wants to be lighter inside material, inside nuclear matter. So what do? We follow the procedure. Now that we know what is the interaction potential for the axion, we follow the procedure we follow for neutrinos. So we have our interaction potential. We can calculate the index of refraction. And it looks like this. It goes like 1 of the velocity of the axion squared. And it's roughly, it turns out by numerical accidents of order 10 minus 8 as well. Very similar to the neutrino one, but that's just by accident. And notice for the particle theorist in the audience that is actually independent of FA. So what enters there is essentially the QCD constant scale, m pion squared times f pion squared, which is kind of like helps a lot. So the axion wavelength that's relevant for the type of setup, you cannot, so I told you about superradiance, and there you needed the QCD action to have the size of astrophysical black holes, which is anything between kilometer and above. Here, though, you need to make slightly smaller than a kilometer. So we need to make, it turns out, the relevant parameter space for this is when the decay constant is around 10 to the 9 GeV. And there the wavelength, the Broly wavelength that's relevant for this, which is roughly tens of centimeters, for around 40 centimeters to be precise. So what does that do? We follow the same procedure as before. The thing that we need to change, though, in our grating is the width of the sticks, okay? So if we keep the length the same, we have a 10-meter structure, and the width is given by the square root of, and the reason what the width changes is because the width of the structure is the wavelength of the particle, the de Broglie wavelength, times the radius of the structure that you want. So if I keep the radius fixed and I increase the wavelength, it means I have to increase W. Okay? So in principle, if you were to use the same structures for the same neutrinos, you'll have to find a way to bring these things together so that they form thicker things if you want to perform the same experiments at the same time. And again, following the same procedure, you can calculate the force for the QCD axion. And this force for FA of 10 to the 9 and a 10-meter uranium structure is actually roughly, you see here, this is 10 to the 25 now. So it's the force is multiplied with 10 to the 25, meaning the force is of order 10 minus 25. So it's 1,000 times bigger than the neutrino. So we've created a situation where dark matter is a huge background for our neutrino search. So this is actually, this is heavier, this is larger than the weight of the proton, thank God for once. So, so it turns out that you can make a plot, a very naive plot, where you show the coupling of the axion to quarks, to QCD, as a function of the axion mass. And this is the line where the QCD axion lies. This is roughly that's excluded by astrophysics, and the standard quantum limit probes this entire range. The reason that we stop here is because then the wavelength becomes larger, like 4 meters. So then it gets a bit silly to consider bigger wavelengths than that, okay? But that's a bias, okay? But it's interesting that the dark matter signal, in fact, can be a background in these experiments for. I should say, though, that there's a funny thing that happens, also that helps the axion. So the change that we create in its density locally is tiny. We're talking on 1 part in 10 to the 5. That's a change in the density that we create. But the density of axion particles, if the decay constant is at 10 to the 9, is 10 to the 11 per centimeter cubed. Just to remind you, for the neutrinos, you had 56 per centimeter cubed. So we're talking, the axions are very dense because they are the dark matter, and their mass is much lighter than the neutrinos. And this is where, actually, yeah. So that's basically all I have to say. And so I want to thank you first for your attention and your questions and your interest in the last 3 days. I hope I showed you that refractive effects can affect significantly the local distribution of the cosmic neutrino background. And you can actually create structure based on these refractive effects to manipulate that distribution at the laboratory scale. It sets a challenge, it definitely sets a challenge. I don't have an experiment. I wish I had an experiment that tell you, okay, this is what you built and you will see tomorrow. No, it will take time. But I think it's going to be a worthwhile journey. And hopefully, we'll get to take a nice picture of a baby universe. So with this, I thank you so much.
Are there questions? Well, I'll ask a question about your axion plot at the end.
Yeah.
So that's assuming that the axions are 100% of the dark matter?
Yep.
Okay. But
in
these
that
are-
range,
These are lower decay constants, so we might expect them to be a bit subdominant.
yeah, thank you for asking that. Yes. So in this case, I have to rely. So if actions were produced through misalignment alone, it wouldn't be enough to give you dark matter in that range. But as you know, there is the post-inflationary scenario where you have production of domain walls and cone Smith rings. And in fact, as you know, there is a lot of work that's been done recently in the topic. And they find that it can greatly enhance, there is huge uncertainties yet, but it can greatly, it pushes the value of the decay constant for which you get the right dark matter abundance, in fact, closer to this range. So this is why I assumed. I mean, you can, it's proportional to the density, so you could scale up and down to see how the scale then goes like the square root of the density, so even if it's 1%, but the key point is that motivates this is this post-inflationary PQ phase transition scenario that motivates this range for dark matter. And I should say it's actually quite hard to do experiments there because there is another issue that this corresponds to frequencies, the traditional searches for action, this corresponds to terahertz frequencies, and there are no good photodetectors there. So it pushes actually, it moves the detection of the action question instead of a high frequency question that it usually, because this would be at terahertz frequencies, it moves it in a different frequency regime altogether. So it's a completely different type of search. Yeah, thanks for asking, yeah.
So similar discussion can be applied for the dark photon, dark matter?
Good, excellent. So I tried to run some quick numbers. The problem with dark photon, dark matter is that all the estimates I've done, some down were giving me small numbers. It's worth someone, because the index of refraction scales like the coupling squared, the mixing squared. So that suppresses it by a bit, so I could never get big enough effects. But I haven't really looked so much. So we didn't really scan all, the one that we thought about, we thought we picked the best one. Just say that. So that's why we stuck to the QCD action. Yeah, but I think it's worthwhile for people to explore what other things you can do with this.
I have to go, but I hope you come back. This was really fun. And
thank you.
Yeah.
Thank you, Melissa.
I haven't had so much fun in a long time in this room. I know I don't need to share that, but I just wanted to share that because I have to leave.
Thank you, Melissa. Thank you, Melissa. It's been fun for me too, guys, and thank you for all your questions. It really makes this process much better.
There are no more questions. Let's thank Mina again.